Hello everyone, welcome back to part 2 of lecture 31. So today we have started the module 9 and this is the second part. So in the first part we have tried to understand the liquefaction, how it happens, why it happens, and now let us understand the effects of liquefaction. So here you can see the effects of liquefactions are excessive strain, foundation settlement, bearing capacity failure, flotation of structures, lateral spreading. So this probably you might have observed in the earlier slides. In part 1 I showed you one video and that was very clear that structures were floating, right. That means it get tilted when soil loses its shear strength. Then lateral flows, loss of support, loss of lateral support, loss of bearing support, right. These are the effects of liquefaction. And this is the map which says the seismic scenarios of Northeast India. And this is from this paper Kyle 2008. It is the seismotectonic map of Northeast India. And here you can see all these points, right. So it says the tectonic activities happening in Northeast India. For more details you can refer to this paper and you will get the legend and everything. When we talk about Northeast India, it is considered in seismic zone 5. In the north it has Indian plate subducting under the Eurasian plate, right. In the east there is an eastern collision subduction Indo-Burmese zone. Then it has strike slip fault along Dauki in Shillong, which is in the northeast India. In addition, there is a Bengal basin and Tripura fold belt. So all together makes it seismic zone 5. And here you can see how it is moving because of the continental drift and it is colliding with the Eurasian plate, and this leads to the formation of Himalayan ranges, right. So this map views of India's northward movement towards the Eurasian plate through time. So here you can see the time is also given. When we talk about the earthquake activities in Northeast India, here is the list. So you can see the earthquake, date, magnitude, epicenter and the reference. So these papers explain these earthquakes. In the year 1869, the Kachar earthquake occurred and this was on 10th January and the magnitude of 7.5. This is 1897 Assam earthquake. This is on 12th June and the magnitude was 8.1. Then we had this 1923 Meghalaya earthquake and this is on 9th September and the magnitude was 7.1. Then we had 1930 Dhubri earthquake. This is on 2nd July and the magnitude was 7.1. Then we had 1943 Assam earthquake and the magnitude was 7.2. Then we had 1947 Arunachal Pradesh earthquake and that was on 29th July and the magnitude was 7.7. Then subsequently 1950 Assam Tibet earthquake, this was with 8.6 magnitude. Then 1984 Silchar earthquake and the magnitude was 6. Then 1988 Indo-Myanmar border earthquake and here it was 7.8. So these were very devastating earthquake. When it is more than 4, we consider it is a huge impact on the structures or the mankind. So 2009 Assam earthquake, we again had 5.1. Then 2016 Imphal earthquake with 6.7 magnitude. And then recently we had this 2021 Assam earthquake with the magnitude of 6. Right. So this explains that northeastern part of India is under the seismic zone 5 and because of the different features present around this area, it makes it very vulnerable, right. So, liquefaction was observed in the Surma Valley of Bangladesh and the Barak Valley of Manipur, and it was because of the Kachar 1869 earthquake. So, here you can see the fissures, the ground fissures was observed, and this was reported by Oldham 1982. Then comes the 1930 Dhubri earthquake, and it caused the liquefaction at West Garo Hills, Meghalaya. And again in 1950 Assam earthquake caused liquefaction at Haldibari site, and here you can see this particular map. This is basically sand dikes, right. So, this is from Haldibari from 1950 Assam earthquake, right. Then sand dikes at Khoang site, and this is from Reddy et al. 2009. So, here you can see they have nicely marked the boundary. So, this is for the sand dikes. Here you have the sand reservoir, cap horizon, root log. So, these are nicely captured in this particular photograph. Then Kalyanala site, it is again from Reddy et al. 2009, and here you can see the presence of sand dikes, right, and this is the source sand. So, how it is getting reached here. So, due to the recent Assam earthquake in April 2021, there was ground fissures noticed near Sonitpur. So, here you can see this particular fissure that was identified, and here also you can see this is very fine grained soil, the fine soil, right, which is not present in the surrounding area. So, this is from Sonitpur, this ground fissures was identified. This is the scenario of liquefaction in northeast India. So, this is from one of my PhD students' work, Rick Chaudhary, and here you can see this Arunachal Pradesh, Assam, Manipur, Meghalaya, Mizoram, Nagaland, Tripura are highlighted with different colors, right. And here you have this liquefaction sites, right. So, when we talk about this factor governing the liquefaction potential, so we need to understand these parameters. The first one is the earthquake intensity, then what was the duration of the earthquake, because if the intensity is high and duration is less, that also causes the damages. But if the intensity is low and the duration is long, then also it will be having major impact. If the intensity is low, duration is low, then probably we will not have that much of impact, but we need to understand the intensity and duration both when we are talking about the liquefaction potential study. So, we have the next parameter, which is the building load. What is the load on the soil on the top layer? Then what is the condition of groundwater table, because subsequently that will interact with the soil column and it will loses its cohesion, right. Then comes the depositional environment. What was the environment of deposition? Aging and cementation of the material, the top layer, the soil column, and then you have the rock. So, subsequently what is happening with the cementation? What kind of cementation is present? Then confining pressure, drainage condition, is there any other way of bringing the water into this soil column? Then you have soil type, because different types of soil have different behavior, they have different engineering property. So, they will have different shear strength. Then soil relative density, particle shape, because particle shape also influences the shear strength. Then particle size distribution. All these factors in a combined way contribute to the chances of soil undergoing liquefaction. So, this is how we analyze the liquefaction potential of a particular soil column. When we talk about the earthquake intensity, The application of external loading such as earthquake loading triggers liquefaction. Hence, the more intensity there is, the greater the chances of liquefaction. So, intensity is one of the parameter. Then duration, if the duration of the earthquake loading is significant, then particle conditions also degrade for repeated loading and pore pressure generation, which will trigger liquefaction. And as we discussed earlier in the previous slide, the building loading, the more the load, the more the chances of liquefaction triggers, right. Then comes the most important parameter, that is groundwater table. The liquefaction phenomena very much depends on the pore pressure generation. If the groundwater table is at significant depth, then there is no scope for pore pressure generation, right. But if the groundwater table is near to the surface, then you are having high chances of liquefaction. Then comes the soil type, because when we are having different types of soil, clay soil, peat soil, sandy soil, silt soil, chalk soil, loamy soil, they have different engineering properties, right. So, the cohesionless soils are prone to liquefaction, that we have also understood in the beginning of the first lecture. If the soil is plastic, that would mean the innate cohesion gives resistance against liquefaction. So, if the soil is plastic, right, then inherent property, that inherently the cohesion will give the resistance against liquefaction. Then comes the relative density. The soil having low relative density signifies that the medium already has very low resistance. In such a scenario, liquefaction triggers quickly. When we talk about particle size distribution, if different size particles are present, then pore between bigger particles can occupy by smaller particles. It will be densely packed and same size particle will have voids. This trigger liquefaction quickly. So, all these parameters have direct impact on the liquefaction potential of the soil column, right. Then the shape will also have the impact, right. You can see the clay and sand. Then aging and cementation. Particles kept at a significantly longer duration will experience cementation and natural packing due to several hydrological processes that will offer resistance to liquefaction. Then when we talk about the confining pressure, so here you can see this particular animation, the more confining pressure will give resistance to liquefaction, because there will be no scope of dissipating the pressure, right. Then comes the drainage condition. So, if the drainage conditions are good, then the pore pressure generated can be dissipated easily and liquefaction can be avoided. When we talk about depositional environment, it also has a significant role. Soil deposits close to a river will have a high groundwater table and the same particle size, which triggers the chances of liquefaction, right. So, here under the different environmental condition, the same soil can have different potential of liquefaction. So, here you can see this is the same video, because this video is nicely explaining the liquefaction theory. So, you can just go through it again. So, here 3 factors requires for liquefaction to occur: loose granular sediment, water saturated sediment and strong shaking, that means the seismic activities. And when you are having the loose granular sediment here, on the interaction with the groundwater and the same time when you are having the seismic activity, what happens? There will be release of the pressure and this soil column will start failing, right. So, this is the actual scenario of San Francisco. With this, I will end the part 2 of liquefaction. So, here you can see I have listed the references. and if you are interested to go in detail of my contents, you can refer these papers and you will get all the details. Thank you very much.